All right, guys. Today we're going to be starting our chapter 4 on quadratic functions and transformations. Again, we have kind of dabbled in this in chapter 2, but I don't want to take anything for granted today, so I want to go ahead and talk about this. Let's talk about the difference between quadratic functions and just regular old functions. And so if you take something like y equals x plus 1, for example. And remember, this is in slope-intercept form, and so we could graph this very easily. And so I'm just going to sketch a little graph here. Again, this positive 1 tells me that that is my y-intercept. So I know that I would have 1 point, let's say, right here. And then in front of this would be my slope. You remember the y equals mx plus b. And so this would be my slope right here. And so I don't have a number here, so it's assumed that there is a 1. So we could think about the fact that this would go up 1 over 1, up 1 over 1 again. And so our line is going to kind of look like this. So that's what a linear function looks like. Again, you can kind of figure that out because it looks exactly like a line. But when we're talking about quadratic functions, actually we're talking about something that would be like, for example, f of x. Now remember, f of x and y are exactly the same thing. So I could have just as easily said y. So f of x or y equals x squared. And so you'll remember what that kind of looks like. And I'm going to skip over to Desmos real quick and just let you see that. So you can see here we have the graph of y equals x squared. And you notice it has this U shape, okay? So that shape is actually called a parabola. And so we talked about different variations of this. And more than anything else, we talked about vertex form, and we talked about how that we could look at that and figure out what kind of transformations have happened. So let's skip back over to our notes here for just a second. And I'm going to go ahead and write out the vertex form of a quadratic function. And so that would be y equals plus or minus a times x minus h squared plus k. Now, you may or may not remember that from what we did in chapter 2. But again, each one of these things plays a particular part in an equation, for example. So this plus or minus, you will recall, tells us whether there is a reflection or not. So again, if this is positive, then this is going to be pointing upward, just like this is in this Desmos graph we did. You notice I've got nothing here, so we've got to assume that's a positive 1, and you notice my graph turns upward, okay? If I go in here to this graph and I put in a negative x squared, notice what happens. My graph actually turns downward, okay? So right here, this in front of that A term determines whether there's a reflection or not. Again, whether that points upward or whether it points downward. So then I'm going to skip over here for just a second because this right here determines whether we have a horizontal change or not. Okay. So if I put something in that same quadratic function, let's go back and let's change this, for example, to just that, but instead I'm going to put parentheses, and we're going to change this. I'm just going to go ahead and write this back out because it was getting pretty messy. All right, I'm going to say x minus 2, and we're going to change that to squared. And notice what happens. I have the same exact graph that I had a few minutes ago. As a matter of fact, I'm going to go ahead and put that other graph up. Remember, that was called a parent graph. So I have the parent graph, which is blue, but you notice this red one is exactly the same graph, but it has moved over to the right 2 spaces. Now notice here, I put in a negative 2, but yet it moved to the right, okay? So when we're talking about horizontal change here, it is the opposite of what you think it may do, okay? Remember that it is the opposite. Now let's talk about this over here. So this over here is our vertical change, okay? Our vertical change is denoted by this K that's out here at the end. So if I take a similar type equation. Matter of fact, let's just change this one. We'll change this to x squared. But instead, at the end this time, we're going to put a positive 3. Notice what happened. I have exactly the same graph. Here's my parent graph, the blue one. I have exactly the same graph with the red one, but you notice that it moved up 3 spaces. Matter of fact, that little point right there tells me that it's 0, 3. Okay, so this denotes a vertical change, and you notice it is literal. In other words, when I put positive 3 here, it actually moved up. So it is literal. So with the vertical change, if I put in there that it needs to go positive 3, then it is really going to go up positive 3. Whereas with a horizontal change, if it says negative 3, it actually goes to the right 3 units, which is the opposite of what we think it ought to do. Okay. Last but certainly not least, this here is my scale factor. And so let's go back to our Desmos graph one more time. And this time we're going to go ahead and keep the x squared, but you notice in front of the x, I'm going to put a 2. And notice what happens. Again, the blue is my parent graph, but the red is the graph with the 2 in front of it in the A position. Okay, so what that did here, that actually made this graph stretch inward. Okay, just like if you were to stand up and stretch your hands, it is stretching inward. Okay, so this denotes a stretch. So if A is greater than 1, it actually causes the graph to stretch. Okay, if A is between 0 and 1, and that's basically what we have wrote here, A is between 0 and 1, then notice what happens. We'll go back to our graph. I know we're flipping back and forth quite a bit, but hopefully you're able to take a look at this and see what's happening. So you notice if I change this to 1/2, now all of a sudden, here's my parent graph, the blue one. The red one is starting to flatten out. Okay, another word we could use for that is compress. And so this A in front of this really helps me determine whether the graph is going to stretch or whether it's going to compress. Okay. So that is just kind of a review from chapter 2. So this is kind of the things you're going to be looking at. You're going to be looking at transformations, but you're also going to be identifying some things within these graphs. So let's go back to Desmos real quick. And I'm going to go ahead and get one of these out of the way. And you notice right here is my parabola shape, y equals x squared, okay? Notice right here, it's kind of giving me a point. I'm going to go ahead and black that in. But notice what's happening. From here, from this side down, this graph is going downhill. And then all of a sudden, right here, at this point, it makes a turn that starts to go back uphill. Okay, that is a very important point. And the name of that point is actually a vertex, okay? So when we're talking about this, let's go ahead and make us another little sketch here. The point where it starts to turn back uphill, this point right here is called a vertex, okay? That is called a vertex. And so there's some other important information that that comes as a result of this that we need to talk about as well. Our axis of symmetry is the point where if I turned this graph, if I turned it completely around, it would land right back on top of itself again, okay? So if you notice, I really have an axis of symmetry right here in this particular graph. And what that means is that, again, if I rotated this graph around, it would end up in exactly the same spot, okay? So for this particular one, axis of symmetry, okay, it is right here. It's this dotted line that I just made up through here. Maybe a little bit hard to see, okay? So that would be my axis of symmetry. You also notice a couple more things about this graph. Notice that this graph goes on forever in this direction, okay? It just keeps going on and on and on and on. But there is a minimum that this graph has, okay? So when we're talking about range, we're talking about where the graph starts and maybe where it stops. Well, in this case, the range, I don't stop when I go this way. So what is a way mathematically I could say that? Well, my range for this particular graph is positive infinity. In other words, it goes to infinity, and infinity just looks like an 8 that's kind of turned on its side, okay? So my range is it's going to infinity, but where does the graph start? Well, you notice my graph here in particular starts at y equals 0, okay? So the first part of my range would be 0. That's where I'm starting at, but then I'm going to positive infinity, okay? And I'm going to use a bracket as well because the bracket indicates that that is my starting point and it includes that point, okay? The reason we put a parenthesis at infinity is because infinity, you never really ever reach infinity. It just keeps going and going and going. Okay, so a couple different things we've talked about here. We've talked about a vertex, which is the point where it really begins to turn the other direction. We've talked about the axis of symmetry, which is that invisible line that goes vertically up and down through the middle of our graph. And then we've talked about the range, which is the starting point for the graph and then where it goes. Okay, so this one went from 0 through infinity. Let's talk about one more concept, which is basically whether this graph has a minimum or a maximum. Well, again, if you think about it, it goes this way through infinity, so it doesn't really have a maximum, but it does, in fact, have a minimum. Okay, so it does have a minimum. And where is that minimum? Well, let's think about the y-axis, because if we're talking about minimum or maximum, we're always talking about where it is up and down, okay? So the fact that it has a minimum, where is this minimum right here? Well, at this particular point, y equals 0, okay? Because on the y-axis, this is actually y equals 0. So that would be our minimum. Our graph, in other words, starts at 0 and it goes up through infinity. So it has a minimum at y equals 0. So this is a type of problems kind of you're going to be working on. I want to skip over to your actual worksheet. We're going to work through a couple of these, and then I'm going to turn you loose for some practice. You only have about 6 or 8 problems today, so not very much that you have to do, but a couple different things we have to identify. So let's look at number 11 here. Number 11 says, what are the vertex, axis of symmetry, maximum or minimum value, domain, and range of each function? Okay, so let's look at this particular one here. And again, we can rewrite this as y equals negative x plus 3 squared minus 2.5. Now, what I'm going to do is I'm going to go ahead and write out our form so that we've got that on hand. So I'm going to do that right here. Y equals plus or minus a x minus h squared plus k, okay? So what I want to do is I'm going to go ahead and graph this so that you can see what this actually looks like. And we're going to identify all this stuff, and you'll start to really see what's happening here. So I'm going to go ahead and skip over, and I'm going to put this on Desmos. And Desmos will definitely be one of your best friends here when you get ready to do this task. So I'm going to go ahead and just type in this problem so that I can see graphically what's really going on. So negative parentheses x plus 3 squared minus 2.5, okay? And I'll go ahead and get this kind of out of the way so that you can see what we've got. Okay, so this is our graph right here. So one of the first things you're going to notice is this graph turned up or is this graph turned down? Okay, well, you'll notice it's turned down. And let's go back and look at our equation here for just a second. You'll kind of see why. Notice there's a negative symbol right there. Okay. Also, you'll notice that this graph is moved to the left 3 units. Well, right here again, we had our horizontal change, which was a positive 3. Remember, the horizontal change is opposite of the way that you think. So instead of going to the right 3, it actually went to the left 3. And then you notice you got negative 2.5. Notice my parent graph always was right here. It started right here. Well, notice I'm down exactly 2.5 units, okay? So again, let's look at what it's asking me for. It's asking me for the vertex, the axis of symmetry, the maximum or minimum value, the domain, and the range. So we're not going to be worried about domain because the domain is the same for any quadratic function. So I'm not really worried about domain at all. All we're really worried about is the range. So let's take a look at this real quick. First, I need to find out where the vertex is. Well, it's really easy when you graph these because you notice this graph is going uphill and then all of a sudden it turns downhill. If I'll bring my cursor right in this area and go ahead and click, you will notice that it goes ahead and tries to find a point for that. So notice the point that it gave us. It gave us -3 and -2.5. -3 and -2.5. Now I want you to look over here at this equation and you'll begin to understand why it's called vertex form. You'll see these numbers actually appear in this form, this original problem that we had. Okay, so let's go back to our notes here for just a second. And what I want you to notice is I figured out that the vertex is -3 and -2.5. Well, notice in my formula, I already had a -h. So in order for this to be a +3, that meant that my original value that went here had to have been a -3. And so that's where this -3 came from. So what I want you to notice is that your vertex is actually h and k, okay? H and k in this form actually denote what your vertex are, okay? So very quickly we can see, again, from graphing and from vertex form, that my vertex is actually this right here. All right, let's talk about our axis of symmetry. So let's go back to our graph real quick. And you'll notice here that we have, imagine an imaginary line that goes right through the middle of this right here. Okay, it always goes through the middle. And that way, if you spin this graph around, it would end up in exactly the same spot. In other words, these two sides would be symmetrical. This side over here would exactly match this side over here. So what would that line be? Well, what is my x coordinate here? My x coordinate is a -3. So matter of fact, I'm going to go ahead and do that. I'm going to say x equals -3. And notice what it does. It puts me that line down through the middle that is my axis of symmetry. So that would be the answer for my axis of symmetry. And I'm going to abbreviate that as AOS. Axis of symmetry is x equals -3. So your axis of symmetry is actually whatever your x coordinate of your vertex is. You see that? So you can see that we're taking one piece of information and we're really able to do a whole lot with it. Okay? Let's also look at this graph really quick. And let's see whether this has a maximum or a minimum. Well, notice it looks like it goes on forever in the negative direction, but it does in fact have a top. Okay? So we can say then that if there is a negative here, we actually will have a maximum. If this was not negative, if it was positive, then we would have a minimum or a trough, okay? So now we can go back over here and we can say it has a maximum. And where is that maximum at? Well, notice the maximum is wherever the top of our graph is. Well, here is the top of our graph, right where we had our vertex, right? So you'll notice that the top, now is it the x coordinate or the y coordinate? Well, if we're talking about a minimum or a maximum, we're talking about how far it is up or down. So it's always our y coordinate. So we have a maximum at y equals -2.5. So our maximum is y equals -2.5. Last but certainly not least, let's talk about our range. Okay, let's talk about our range. So again, this particular graph goes on forever in the negative direction, but you notice that it does in fact have a top, right? This is the top of the graph where it really starts. So the graph really starts here and it goes down negative to negative infinity. It never stops, okay? So if we're talking about the range of this particular graph, then we're saying that it goes from -2.5 is where it starts. And I'm going to go ahead and change this to a bracket because it actually includes that value, -2.5. And it goes to negative infinity. Okay? Actually, I'm sorry, I messed this up. You know that teachers actually do mess up. Okay? So actually this particular graph goes from negative infinity to negative 2.5. Negative 2.5 is my top section. Negative infinity is the bottom, right? It's the bottom of my graph. So this is incorrect. So this should actually be the correct answer, okay? Again, the graph will really help you, and it will help you to try to figure out exactly what's going on with these, and you'll be able to answer these. Now, these are multiple choice questions, so it's not gonna be as difficult maybe as trying to do this by hand. All right, two more things we need to look at really quickly. So I want to go ahead and look at a graph here, and we're going to look at number 18. I'm going to look at number 18, and in this case, they're giving us a graph, and we have to try to figure out what that graph really is, what the equation of that graph would be. So first of all, let's start writing out our form for just a second. Y equals plus or minus a times x minus h squared plus k, okay? So there is our form that we've been using for these. So the first thing, let's decide. Notice this graph, is it pointing upward? Is it pointing downward? Well, it's pointing upward. So that means that that has to be positive. So we know then that we've got y equals, and we can just leave that as blank because we know that a blank there would mean it is positive. The second thing is we need to think about whether this graph looks like our parent graph or not. So remember our parent graph, if we look at that one more time, we'll go ahead and get rid of these other ones. And we look at y equals x squared. Notice that our parent graph always goes through 0, 0. Okay, if we look back at our problem, you will notice that this one is not at 0, 0. As a matter of fact, right here is 0, 0. But it is actually skewed to the left. Now let's think about a horizontal change. With a horizontal change, it's not literal. So in other words, it does the opposite of what we think. So if it went to the negative direction and -4, then what do you think we need to write up here? So it does have a horizontal change. So we're going to go ahead and say x something, but instead of going to the -4, it is actually +4, okay? So x plus 4 squared, because the horizontal change is opposite of the way we think. Now, last but certainly not least, did this graph have a vertical change? Well, again, normally our vertex is right here, but you notice our vertex is actually up 1 unit. And you'll also remember that the vertical change is literal. So if it's up 1 unit, then it would be +1, okay? And so the other thing we have to figure out is whether we actually had a stretch or a compress. And here's the way you do this. So you start here, and you notice we go up 1 unit and we go over 1 unit. So that means this has a slope of 1. So that means that there would just be a 1 right here, which means there's not really a stretch or compress. Okay, one way that we can make sure our answer is correct is we could also go back to our graph. We could go ahead and put this problem in and put our solution in rather. So x plus 4 squared plus 1. Here's what our graph looks like, and then here's what our problem looks like. So you notice those look exactly the same. I come over to -4, I come up to +1, and if I look at my graph here, it's exactly what I have. I come over to -4 and I go up 1. Notice my vertex is exactly the same as it is in the graph that we had just a few minutes ago. So that's one of the tasks you're going to have to be able to do as well, is to take a graph and make it into the actual equation, okay? Again, Desmos will be one of your best tools that you can use here to be able to do this. So last but certainly not least, let's look at number 21. It says write the equation of each parabola in vertex form. And it's given us, number 21 here is giving us this vertex and this point, okay? So what I'm going to do right now is I'm going to go ahead and write out our form one more time. F of x, I'm using that this time instead of y, just to let you know that you can use that interchangeably, equals a times x minus h squared plus k, okay? And we're going to try to fill in everything that that we can possibly find in this equation, okay? So f of x is the same thing as y. Notice here, our vertex, we said that this point in our vertex is h, and this point is k. And we said that this, obviously this point is an xy coordinate, so I could go ahead and label those as x and y. And so now I can go ahead and begin to put in the information that I've been given. So you notice my y coordinate is -5. We said that f of x is the same thing as y, so I could put a -5 right there, okay? My a, I don't really know. There's nothing up here that identifies a, so I'm going to go ahead and leave that as it is, a. Now I can go ahead and put in this value of x, right? My value of x is -2 minus, that minus is part of my formula, h is -3. So I've got minus a -3. So I'm just going to write it out like this now, and then we'll clean it up here in just a minute. Squared plus k. So my value for k is actually 7. Okay. So now here's what I'm left with. I've got -5 equals a. And let's go ahead and clean this up. -2 minus a -3. We would keep change. So -2 plus. So that is going to become -2 plus 3, which is actually 1. So 1 squared plus 7. Okay. So let's think about what we have. We've got 1 squared, which is just 1 times a. So 1 times a is really just a. So I'm going to move my work right over here. So I have -5 equals a plus 7. Okay, so the last step I have to do is I have to subtract 7 from both sides, which gives me, I'm going to move my work over. I'm running out of room. A equals -12. So now I can put all of this stuff back into my original equation that I started with. So we're going to go back over here. Actually, I'm going to go back up. So I've got f of x equals, again, what was my a term that I figured out right here? My a term was -12. So I'm going to go ahead and put -12 right there. X minus, now think about this, it was minus a -3, right? So instead of a -3, it's actually going to be +3, and that's always squared, plus k, and what was my value for k? My value for k right here is +7. So this would be my equation that I would need, okay? And again, one more way that you could do this real quick is you could go to Desmos, and you're going to have those answers there on your page that you're looking at. I'm going to go ahead and test my equation. It's a good way to kind of think about this is you're testing your equation to see if it's actually going to work. So there we are. What is this point? My vertex is -3, 7. You'll notice from my problem, that's what my vertex should have been. My other point should have been at -2, -5. So let's see if this graph actually goes through -2, -5. So if I go to -2 and -5 on my graph, you will notice that right there it is, -2, -5. And so this would be the correct answer for that particular problem for number 21. So again, you've only got about 6 of these. If you need help, please ask for it. Please, please, please. I know this is kind of an arduous subject, and so it may be a little bit difficult to understand. If you need help, I'm saying please ask for that help, and we'll do our best to try to help you get through this today. Thank you.